Hi, today we're going to do a review and teardown of another piece of test equipment from Peak Electronic Design in the UK. So today we're going to be looking at the LCR45 meter, which is a LCR and impedance meter, and this was kindly provided to me by Jeremy Siddons, so a big thank you to Jeremy, who's the CEO at Peak Electronics Design in the UK. We're going to have a look at the operation of the unit, and then we're going to take it apart and have a look inside and see what the various circuitry does. We'll also do a quick comparison of why you might want to get an LCR meter from Peak Electronics Design, or indeed a more advanced LCR meter than, for example, the ranges that are built into your multimeter or into something like this low-cost LCR meter from Tenma. So let's go down to the bench and have a look how this works. And we'll probably just do a little bit of theory on complex impedance, and then we'll measure some inductors. We might even make one, because I do need to make one for a project that's upcoming, and then we'll have a look inside. So let's go down to the bench. So here we have the LCR45 LCR and impedance meter, and it has the same form factor as the other devices in the Peak Electronic Design range. So it's the same form factor as the ESR70 and DCA75 Pro, which I recently reviewed. If you've not watched those videos, the links are down below. And it's basically a kidney-shaped kind of palm-sized device, just with a simple 2-button operation. On the front of this meter, we've got the 2x16 display, which is really quite readable, but if you watch the other videos, you'll notice that I did feel that these could really do with some kind of tilting bail, because basically this sits flat on the workbench and you can perfectly read the LCD from above, but when you're viewing it from the side, you do end up with a bit of a shadow cast at the top of the display, which makes it slightly less readable. So recently Jeremy was on the EEV blog forums where we were discussing some of these devices, and the link for that is just here. And he came up with a design that we could 3D print, which basically clipped into these 2 points here, and it would mean that this could be freestanding on the desk without needing anything else to prop it up into a nice position. So I don't think there's any plans for them to commercially produce any of those stands, because the order quantities are actually going to be quite low, I would have thought. So there are some 3D printable files, so if you've got a 3D printer, you can download those files and make a nice little holder which will hold them in place. So I may have a chat with some of the guys at the machine shop at work and see if they can manufacture something from those files. So that's really good to see that they've listened to some feedback and come up with a solution in actually really quite a short period of time, which is really great to see from a manufacturer of such devices. So yeah, a big thumbs up for actually listening to the customers and coming up with a solution. So let's just have a quick look at the technical specifications of this unit before we have a look at the operation of how it actually works. So as it's an LCR meter, it can obviously read resistance, capacitance and inductance. So the ranges for resistance are 0 to 2 megohms with a resolution typically of 0.2 ohms, and the accuracy is 1% plus or minus 0.6 ohms. In the capacitance range, it can read from 0 picofarads up to 10,000 microfarads, with a typical resolution of 0.2 picofarads and an accuracy of 1.5% plus or minus 0.6 picofarads. And then in the inductance range, from 0 microhenries all the way up to 10 henries, with a resolution of 0.2 microhenries, and the accuracy here is 1.5% plus or minus 0.6 microhenries. And then we have the passive component impedance. So for the real and imaginary parts, when you're reading the impedance, it has an accuracy of 1.5% plus or minus 10 least significant digits. The magnitude when reading the impedance is 1.5% plus or minus 10 least significant digits. And for the phase measurement, we've got a plus or minus 5-degree accuracy. And it reads the actual values of impedance and LCR at a rate of 1.5 Hz, although there is a bit of tolerance on that. And the maximum voltage that you're going to see on the test probes is plus or minus 1.05 volts, and a maximum current of plus or minus 3.25 milliamps. So some of this will make a bit more sense when we have a look through the manual at how this device actually measures complex impedance. But this meter can measure the complex impedance of components which are attached to the test probes, and that involves a frequency component. So we have a specification here for test frequency accuracy, and it's giving us a value of plus or minus 0.5%. And here it says the sine purity specification, so it's clearly injecting a sine wave into the component, and the specification here is minus 60 dBs at the third harmonic, and then we have the operating temperature range of 10 to 40 degrees C. And this device takes the same GP23A battery that was in the ESR70. So it's a 12 volt small battery, and it will actually run from 8.5 volts up to 13 volts, although in a future revision of this device it might be nice to see a AAA battery with a DC to DC converter on the board, similar to the DCA75. So there we have the specifications of the LCR45, and as you can see, the accuracy specifications are good enough for the majority of components that you're likely to want to test on this device. Obviously, with things like the resistance range, something like a Fluke 87V is going to have a much more accurate reading because it has a much more accurate reference and resistor network within it. But for things like inductance and complex impedance, those things you can't normally do on a multimeter, so this is where you'd start to want to use something like a dedicated LCR meter. And then if you look at something like the Tenma, so here we've got the Tenma 728155 LCR meter, and this retails for about £28 excluding VAT, so that's about just over a third of the price of the LCR45. But this is really basic, so it's fully manual ranging. It only measures the resistance, inductance or capacitance. It doesn't give any complex impedance measurement, and the specifications of this device are quite poor. I think the inductance is about 2% accurate plus 8 digits, and really this doesn't offer anything more than something like some multimeters will have built in. So here we've got the Meterman 37XR, which I think has been rebranded now, but this already has inductance and capacitance and resistance ranges, and this was, at the time, I think I only paid £80 for this, although now it's retailing for almost double that. But some of the basic multimeters will do as much as the Tenma LCR meter, plus obviously it has the voltage measurement and current measurement. So this device is kind of pointless at its price point when you can get fully featured multimeters that do LCR measurements anyway. So I've just pulled out some components from my component drawers, and we'll just have a go at measuring some inductance, capacitance and resistance values just to see how this device actually works. So you can use it in a fully automatic mode where it detects what it thinks the component is attached to the leads. This may get confused on something like a wire-wound resistor, which is a coil of wire. It may start to think that's an inductor at certain values, so then you can set it into a manual ranging mode. But if we turn on the device, you will notice that it did actually say calibration due 2016, so there are clearly some components in here which may drift with age, so if you want to keep it on specification you do need to send it back for calibration, although just for indication purposes most of the time this is going to be accurate. So if we try measuring a capacitor, you do need to make sure that your capacitor is discharged before you test, although you'd hope that there is some protection circuitry inside just to make sure that it doesn't damage the front end. But we've got a little capacitor here. I don't know what value this is, but if we hook it up, you can see here it's reading 2 nanofarads, and it's measuring that at 15 kilohertz. So if you look in the manual, you can see actually that it depends on the capacitance value as to what frequency range it measures at. So if we switch that out for a much bigger capacitor, so let's try this electrolytic, which I've got here. So that's reading about 500 microfarads, but it's measuring that at DC now. So this is beyond the range where it's able to read these at an AC frequency. It's just reading this at DC. And then if we press the enter button, I think you can scroll down and get a bit more details. Obviously, as this is measuring at DC, There's no impedance value that it can measure. It's basically a capacitor blocking DC, so there's a high impedance there. No admittance value, and obviously it can't do the magnitude or phase or anything like that because it's still measuring at DC. However, if we switch that back out for this capacitor, we should see some numbers being populated there. So here we can see our complex impedance at 15 kilohertz, which is 150 ohms, and then the imaginary part is 5.28 kiloohms. The admittance value in microsiemens, and then we've got the magnitude and phase, 5.28 kiloohms at minus 88 degrees. So I'll explain a bit more about that later. We'll have a quick look through this manual to understand what those numbers actually mean. But you can see now if we try and measure a resistor, it should automatically switch from capacitance to resistance. So we'll see what it does here with this metal film resistor, and that's immediately detected it's a resistor, 15.01 kiloohms, and it's measuring that at DC again. And we don't get any of the complex details there because it's measuring at DC. Now if we look at a inductor, so I've got here a common mode choke, but we can measure just one side of it and it should behave like an inductor. So if we attach these to the leads, hopefully I'll get the right ones. And you can see now it's detected that's an inductor. The DC impedance is 0.22 ohms. The inductance value is 20 millihenries, and it's measured it at 1 kilohertz. So if we scroll down, we can see the complex impedance here at 1 kilohertz of 2 ohms, and the imaginary part 125 ohms. And we've got the admittance values again, magnitude and phase, so 125 ohms, a phase of 89 degrees, and then we can scroll back round to the information about this inductor. And then we'll just have a quick look at this power inductor. So this is a Worth Electronic 22 microhenry inductor, and I think this is rated for probably about 5 amps, so it should have a nice low DC resistance value. So this doesn't have any legs, so we'll have to take off the clips. But these clips are joined by 2mm banana plugs, and you can buy some probes off the Peak Electronics website, which I don't own at the moment, but it just means that you can probe things a little bit easier. But if I hold these down onto the inductor, you can see the DC impedance here of 0.02 ohms. It's measured the inductance at almost 20 microhenries, and it's measuring that at 200 kilohertz. And then if we look down, we've got the complex impedance, so 1 ohm, and the imaginary part is 24.75 ohms. And then we've got the admittance of 1.725 millisiemens, and the imaginary part is 40 millisiemens. And then finally we've just got the magnitude and phase of 24.79 ohms at 88 degrees. So you can see this is really easy to use, and if you just want to quickly measure a device, you can quickly attach a device to it. It does all the auto ranging itself on the majority of components, and you just get all the information you need, and you can just scroll through like you can on the ESR70 and the DCA75. So it's really easy to use. I don't know whether we'll be able to find a component that's going to confuse it. So we've got some larger power resistors here, and these are wire round. So let's have a look and see if it can confuse it. I don't know if it will or not. So it's saying inductor resistor, so it's not sure which it is. It's measuring a impedance of a DC resistance of 0.96 ohms, and it is a 1 ohm resistor, but we've got a bit of an inductive element to it, so it's reading 0.03 microhenries at 200 kilohertz. And again, we've got all the details associated with that. But you can set it into a manual ranging mode. So if it is getting completely confused, you can just set it to a resistor if you know you're going to be measuring a whole load of resistors. So, that's really easy to use. So let's have a little look a bit more about complex impedance in the manual. And then let's have a go at winding an inductor, because I do actually need one for a project. And we'll just see how this can help us. So here we have a section from the LCR45 user guide which is explaining exactly what complex impedance is. So you'll be familiar with resistors which have a fairly constant resistance over a wide range of frequencies, but capacitors and inductors have a impedance which varies quite widely depending on the frequency of the signal passing through it. So a convenient way of representing this frequency relationship is with a complex number. So this argon diagram is showing that inductors and capacitors have both a real element here, which is the resistive element of the component, and then an imaginary part, which is the reactive component of the capacitor or inductor. So the way we calculate impedance for capacitors and inductors is by summing both the resistive and reactive parts of the component. So here we have the impedance equals R plus JX, and basically for inductors, by doing a bit of trigonometry, we can arrive at the equation of Z equals J omega L, and for capacitors, Z equals minus J over omega C. And if you actually want to work with frequencies, you can replace the omega with 2 pi f. And then also by doing trigonometry, we can find out the magnitude here, which is the sum of the squares of the real and imaginary parts, and then the square root of that, and that gives us the magnitude. And then by doing some trigonometry again, we have the phase, which is tan theta equals x over r. And you'll notice that this diagram shows that for inductors, the phase is typically positive, and for capacitors, it's negative. And then we can have a quick look through the manual. So the manual shows you how to turn on and off the device, how to hold the display. So you'll notice that the display was constantly updating, but if you didn't want it to change, you can hold the display and it will just fix what's displayed on there. And then you have the various modes. So we were using it in fully automatic mode, and that automatically detects what the component is attached to the device, and then it gives you the various screens. So we had the component display, the impedance, the admittance, which is the inverse of complex impedance measured in Siemens, and then we have the magnitude and phase display, and it says here an ideal capacitor has a minus 90 degree phase, an ideal inductor has plus 90 degree phase, and an ideal resistor has a 0 degree phase. But in real life, these numbers aren't exactly minus 90, plus 90 or 0, because losses in the inductors and capacitors have an effect on the phase value here. And then it's just explaining how you calculate the magnitude of impedance just using Pythagoras. And then you have the various measurement screens which you can scroll through, which we did earlier. You can also change the LCR from the fully automatic mode into manual mode, so you can switch it to inductance, capacitance, resistance if the LCR meter is getting confused with the component that you're measuring. And then you'll see there's also compensation here. So if we scroll through the manual, you'll see that you can do probe compensation to remove any of the artifacts that the probes may introduce into the readings. And then we have the test frequency mode selection. So in automatic mode, it will generally just select a suitable frequency to test the component at, but if you know that your component is more suited to a particular frequency and you're going to be using it in that frequency range, you can manually select the frequency that it does the test at, and you can see here how you're allowed to change the frequency depending on the component value that you're reading. So for a 300 picofarad capacitor, you can actually test it at 215 or 1 kilohertz, and there's also similar for inductors. And then just finally, there's a section towards the end just showing how you take care of the LCR45, how you know when the battery is going low and how to replace that. And there's also some self-tests which are built in, and it will give you an error code. So earlier on I mentioned I wanted to wind some inductors for an upcoming project. However, I can't find the magnet wire, but we'll still wind an inductor just for example's sake. So we have the inductor core here, and this has an inductance factor of 6970 nanohenries. And with this simple equation here, we can work out the number of turns required on this toroidal core just to create the inductance that we want. So let's say we wanted a 180 microhenry inductor. If we plug those numbers into here, it tells us we need 5.08 turns. Now there is a tolerance on this number, so I think the the core itself has a tolerance of plus or minus 20%, so this isn't going to be spot on to give us 180 microhenries, but we can just verify the result with the LCR meter. So we'll attach one clip to one end of the wire, and then each pass through the core counts as one turn. So that's one turn there. 2, 3, 4, and the 5th turn there. And if we attach this to the other clip and turn on the LCR meter, we can see the inductance reading about 163 microhenries, which is fairly close to the 180 microhenries and within 20% tolerance. So that's just a quick way of verifying any inductors that you've wound are actually reading the value that you'd hope. And then the final thing left for us to do with the LCR45 is to take it apart and have a look what's inside. So the construction of this LCR meter is very similar to the other devices from Peak Electronics. So we've got the coaxial cable coming in at the bottom left here, so it's nice to see coax being used just to maintain signal integrity at the higher test frequencies that this device uses. At the bottom left here we've got some signal clamping here right at the input, so this is to try and help protect against some voltages being present on the test clips, but it's not going to be able to sustain any voltages for any sustained period of time because it's basically limited by the power dissipation of these diodes here. At the heart of the device we've got a PIC 16F1788, and this is really quite an interesting device. So it's got a lot of peripherals which are really suited to use in an LCR meter. So we've got a 12-bit ADC, we've got a 16-bit PWM, we've got an 8-bit DAC and a 5-bit DAC, so this will be able to produce some really good waveforms for measuring the inductance and capacitance values. So we might have a quick look on the scope just to see how it does its tests after we've had a look inside. And then on the right here we've got some op amps. So we've got the microchip MCP6L04, which is a rail-to-rail quad op amp. We've got another one just here. And then in the middle here we've got a quad bilateral switch, and then we've got a slightly better specified op amp, so this is probably right on the input from the test leads, and this is an MCP6284, which has a slightly higher gain bandwidth of 5 MHz, but again this is a quad op amp. And then just here we've got some 4000 series logic, so we've got 3 HC4051s, which are 8-channel analog multiplexers. But really, the microchip part here is going to be doing a lot of work here, so it's going to be trying to drive the output to create that sine wave, and then it's going to be using that high resolution ADC to take the readings back into the digital domain. Then if we just have a look at the front of the device, this is pretty similar to the others as well. So we've just got the 2x16 LCD on the front. We've got that battery which fits through the PCB to try and save a bit of bulk from one side of the board. We've got the 2 operational buttons here, and again the in-circuit programming header on the left hand side. And this board has Jeremy Siddon's name on there, along with a date 2002/2014, so presumably this was originally designed back in 2002 and this was manufactured in 2014. But again, we've got really good construction. Let's just have a quick look closer at the PCB. So you can see the reflow on all of these parts is really nicely done. We've got a nice solder fillet on all of the IC pins, and all of these 0603 parts are really nicely soldered. There's no flux residue or anything like that. It's just generally nicely been assembled all over the PCB. And I missed this off from the initial inspection, but we've got some components here around the battery, so we've clearly got some reverse protection going on here. But although the microcontroller is an XLP part, they may well be doing some switching here to turn off the power to the entire PCB under microcontroller control. So what could be happening is the power button may feed into some of these transistors to initially provide power to the board as long as the button's pressed on. And then once the microcontroller turns on and starts running, it may latch the transistor on so it stays on until it releases that line when it goes back to sleep. And at the top left here, after the power circuitry, we've got a 100 microfarad capacitor which is doing a bit of bulk storage. And then towards the bottom here we've got a linear regulator, so there's no switching regulator on this board, so this is just dropping the 12 volts down to the supply voltages for the various logic on the PCB. And then again after that we have a 100 microfarad capacitor doing a bit of bulk storage at the 3 or 5 volts that the rest of the circuitry is running on. And then just at the top of the PCB here we have where the LCD comes through the PCB to connect into the microcontroller, and we have what I presume to be the contrast setting resistors here, and either this capacitor is just filtering the contrast line, or that's a bit of decoupling on the power supply to the LCD. So one thing I would potentially like to see on future revisions of this device is maybe a slightly better cord grip for the cable coming in from the clips. So you can see here they've applied some heat shrink to the coax, and it has actually gripped it quite tightly between the two sides of the shell, but particularly on the DCA75, those three wires look like they were quite prone to accidentally being pulled out. The coax here actually looks like it's quite rigidly attached, but it would be nice to see a slightly better strain relief and cord grip of some kind. But overall, the construction of the LCR meter is really not bad at all. This PCB is on revision 2.5, so it'd be interesting to know how it's progressed from its early design. But yeah, it's really nicely produced, the board's nicely milled out, all of the components again are quality components that they've used on the PCB, and overall it just seems to be a really nicely designed piece of kit. Presumably the calibration which it warns about when you turn it on is fully digital, so this is presumably just calibration that they do with some parameters that are stored on the internal EEPROM on the microcontroller. There doesn't seem to be any potentiometers or anything like that to tweak. So let's reassemble the device, and we'll just quickly hook it up to the oscilloscope and see what it does when it's actually measuring a component. So I've just hooked the oscilloscope up to the LCR meter, and currently there's no component attached. So I'll turn on the LCR meter and we'll have a look at the waveforms with nothing there. It's just turned on now. It thinks there's a capacitor attached, which is probably the capacitance of the scope probe. But you can see it's doing a test every, that's about 2 Hz or so, which is about the update rate of the display on the system, so it's presumably taking close to 2 samples per second. But you can see already that the sine wave is a really nice sine wave, really smooth, so I'm not sure whether they're using the PWM, the high frequency PWM with a low pass filter to create the sine wave, or whether they're using the DAC, or whether indeed they're just using one of the op amps to create a sine wave output. But that's a really nice quality sine wave. And if we zoom out slightly, we can see it's actually doing quite a lot. Presumably some of this is trying to detect if a new component has been attached, and then we've got the measurement section here. So let's see if I can attach this inductor to the probes while the oscilloscope's still attached. And I think it's just turned off now, which is why the waveform has changed. So I've just attached the inductor to the LCR meter, so I'll just turn the LCR meter back on again. It does turn off after about a minute or so. And you can see again it's creating a sine wave. The amplitude has decreased, presumably because the inductor has quite a low DC resistance. But it's still creating the sine wave, and it's kind of at probably about 2 Hz again. The overall frequency of the sine wave obviously is 200 kHz. You can see it just popping up at the bottom left here. But presumably what it's doing is it's injecting a sine wave at 200 kHz, and then it's reading back to see if the sine wave is leading or lagging, which will tell it whether it's an inductor or capacitor, or if it's just a resistor. The received signal will be exactly in phase with the sine wave that it produced. So I hope you enjoyed that review and teardown of the Peak Electronics LCR45. This retails for about £90 including VAT on the Peak Electronics website. I think they charge a couple of pounds for delivery within the UK. You can also buy it from Rapid and Farnell and various other distributors worldwide. In terms of the price point, there's not really a lot that competes, so Cheaper than that, we've got the Tenma, which is about £35 including VAT. Then you've got the Peak Electronics, obviously around £90 including VAT. And then there's not really anything there until about £200 plus VAT for the BK Precision, and then at £400 plus VAT there's a Keysight LCR meter, and that does offer a bit more precision, but if you want even more precision then really you're looking at an LCR bridge, which is a whole different piece of equipment and several £1,000s worth of investment. So I'd really recommend that you buy one of these for your workbench. At £90 it's affordable enough for the semi-serious hobbyist, probably not suitable for the beginner, but a beginner will probably be happy with a multimeter and the functionality that that provides on the LCR ranges. But yes, I'd definitely recommend this device. It's really well built in the UK, which is obviously excellent, and the CEO is obviously deeply involved in the business. He's got his name on the PCB, so he's obviously done some of the electronics design, so definitely gets a thumbs up from me. So if you enjoyed watching this video, please give a thumbs up, don't forget to subscribe if you haven't already, and thanks for watching.